How about now? Good. Okay. And so let me give you a share screen. Okay. Okay, so I'm going to share the screen with you. Let me open up the screen. Okay, there you are. And we're going to go to Alex. All right. Hey, our assignments. And we're going to go to week 9. All right. All right. Everybody can see the homework that you see there? Yeah. Okay, so we're looking at hypothesis tests for today. So let me make the screens one size over here and give it a little shot over here. So, all right. Okay. All right, so here we are. If you look at this is hypothesis test for population mean for this example. So I'm going to go ahead and pop open a question here.
I'm sorry to interrupt you. I don't see your screen, but maybe it's just me. I don't know. I just see you.
Okay, do you see it now?
No. Let me change my view. Maybe it's my view.
And let me take myself off video. Maybe that's also part of the problem. Is that helping?
Not for me. I don't know. Maybe I can leave and come back. Let me try that.
Go ahead and do that. Jacqueline, can you see my screen entirely?
Yeah, I can.
You can see both the Excel and the
Mhm.
question. Okay. Good.
Yes, ma'am.
Anybody else? Everybody else can see it? Yeah.
Good.
Okay. I'll give her a moment to come back and let's read the question together. So in this question, this is basically we're doing a t-test in this case. If you notice on top, it says hypothesis test for the population mean, and it's a t-test. You'll know it because they're giving you the standard deviation of the sample. Do you notice this in the question? They're giving the standard deviation of the sample. They're giving you the actual sample mean, not the actual mean. The population mean is secondary. I know it sounds confusing, but in this case, let's read the question together and let's make sense of it. So the heights were measured for a random sample of 16 plants grown while being treated with a particular treatment. And then it says further from there, let's open it up. The sample mean, that is the key word. Do you see that? The sample mean and the sample standard deviation. Do you see that? they're already telling you that that is going to be 33 and 7 meters. So right here, they're giving you the random sample and the sample mean. They said 16 pairs, 16 is good. This is 16 in total. The sample mean was 33, so we're going to put 33 where the 65 is. And the sample standard deviation, instead of 9, we're going to put 7. And now what they're testing this against, they're saying assume that the proportion of heights of treated plants normally distributed with a mean mu based on a sample can be concluded that mu is different from 38 centimeters. So they're saying this is 38. So instead of 70, we're going to put that as 38. All right. And so since we're looking up here, this is our value, negative 2.857. Now you want to pay attention here. They want us to perform a two-tailed test. Two-tailed means obviously we have a split alpha value. So in this case, let me pop this open just a little bit more. In this case, let's see, we have here, we're going to say mu is equal to 38, or mu is not equal to 38. Why do we use not equal to?
Because it's different from 38 centimeters.
It's different. That's all we know. And this 0.05 level of significance is not going to be 0.05 because it's two-tailed. We're looking at, in this case, you're going to go equals 0.05 divided by 2, which is going to be 0.025, or it's going to be equal to 1 minus 0.025. It's going to be one of those two values. But in this case, we're looking at t-tests. So it's not going to be just that value. In this case, it's going to be equal to t dot. You want the dot. We're going to say t dot inverse. We're going to go probability 0.025, comma. And then we're going to select this cell here. And that's going to be the lowercase value. In this case, you want the upper value equals t dot inverse. Again, you want the 0.975 comma and the 15, and you get the positive 2.315, because one is going to be the low value, one is going to be the high value. So this is like t is greater than, like here the t is greater than, for this t is greater than the value here, t is less than the value. Think of it that way. Okay, so the test statistic obviously is the t-test. Degrees of freedom, obviously 15, right? Because it's n minus 1. N minus 1. If there's anything that I'm saying that is sounding weird to you, talk to me. So the t-test, we're going to do 2.857. Okay. And now the two critical values that we're going to use are going to be negative 2.13, negative 2.13, and we're going to use positive 2.13. Right now, I need you to stop. I need you to think about this for a minute. Look at what I've written down and ask questions, whatever questions you have. I'm going to move this over and this over a little bit so you can see everything. What do you have questions about? I know you have questions. Come on, I know you do. So I'm asking you to tell me what you're, I'm gonna draw a line here. We're looking above this line. No questions?
I think I have a question about your I think it's column E.
Uh-huh.
I just, I kind of missed, no, I don't, maybe I did, because it said the confidence was what, 0.05?
0.05. So I divided 0.05 by 2,
Okay,
and here I subtracted 1 minus that value.
okay.
So, and then the top value is gonna be the positive and versus the negative of it.
Hold up. So for E4, you just did 1 minus
1
the.
minus.
Oh, okay. Yeah, that's the part I
0.025.
had a question about too. So I was like, kind of.
Literally, just type, look at the top up here. Do you see where it says equals 1 minus E3?
Okay.
That's literally all I do. And here, I want you to notice these values up here. This is T dot inverse. You're going to do the E3 comma, and you're going to do the C3 because we're looking at the degrees of freedom. That's this. That's the D of F.
Does the order of it matter?
In terms of
Like, so because you did E3,
comma, C3. Yeah,
right.
yes, it does. Because look, when you do this, you see how it says T dot inverse and then it says give me the probability and then give me the degrees of freedom?
Yes.
So the probability is the 0.025, comma, and the degrees of freedom is right here in the pink. Make
Okay.
sense?
Yes.
Then when you do the 1 minus, it becomes this. It becomes E4, comma, C3. It's still C3 because C3 doesn't change. That's the degrees of freedom.
Okay.
Okay, what other questions do you have so far? So you want to see how well we did this? Well, we have to do this one here. At the 0.05 level of significance, can we conclude that the population mean of treated plants is different from 38? So in this case, what do you think? Yes or no? The rule of thumb is if P is less than alpha, we reject the null. Alpha is going to be 0.025. Our p-value, if you want think about this, what is the p-value going to be if I do inverse of the dist? If I say equals T dot dist, okay, T dot dist, I want to select the z-score, which we're going to get the t value. We're going to get the degrees of freedom, and then we're going to say yes, it's true. We want the cumulative value. Is p less than alpha? Is this p-value less than alpha?
Yes.
P-value alpha. So if we reject the null hypothesis, which is what the conclusion would be here, we would say yes to this, right? Let's see how we're correct. They said C is incorrect. What is the test statistics? The value here is not negative. That's negative, yes, that's correct. Is that correct now? You see how we're good? So take a look at that. Take a look at what we've done. Ask yourself what questions you have. If you have a question, if you don't have a question, we'll move on to the next one.
I don't have a question. I just need to see it again. That's all.
You want to do another one?
Yes, please.
Okay. Is that everybody?
Yes,
Yes.
please.
Yes.
Yeah, okay, let's go to another one. So again, you're looking for a t-value for proportion. Here we go. They're looking at greater than. So we agree so far? Do you see how there's a mean of 40 hours? It seems that these days, the college students who are employed full-time work more than 40 hours a week. That seems to be the mean. Data are available that can help us decide if this is true. The survey was recently sent to a group of adult students selected at random. There were 18 respondents. That's a random sample size. When they did this, they said the mean hours that they worked was 42 with a standard deviation of 9 hours. So those are the only things you need to change right here are the mean, the random sample, the sample mean, and the sample standard deviation. The stuff that I'm going to highlight right now in yellow. That is the only stuff you need to change. The degree of freedom is calculated for you. So it's 17. The t-test is already done for you. Which if you notice, it's a sample mean minus the mean itself divided by this standard deviation divided by the square root of, I'm sorry, divided by the standard deviation divided by the sample size, which is 18. And you get 0.943. Are you getting that?
Yes. Can you show me how you got D5? I think when I
D5? D5? This
Yeah.
right here?
Yep.
This is t.dist. This gives you the p-value of 0.943. So if I highlight it, this is what it looks like. T dot dist. And then there you're taking the D4, comma, the C3, and then hitting true.
Thank you.
Okay, so in this case, what is this gonna look like? What are we gonna put here? What is the null hypothesis? What is the alternative hypothesis? What are they asking? Assume that the population of hours worked per week by college graduates employed full-time is normally distributed with a mean mu. Can we conclude that the mu is greater than 40 hours? So we're going to begin with mu is equal to 40 hours. The alternative hypothesis, which never includes equality, is mu is greater than 40 hours. Okay, what test is this? The t-test. How many degrees of freedom do we have?
17.
17. What is the value of the test statistic?
Is that the 0.943?
0.943. So we're going to go 0.943.
Right, you typing it in the wrong thing.
0.943. Okay, and what's our p-value? That's where this number comes in. I don't know what it did this.
0.82087.
Yeah. It's going to be 0.820507. Yeah. And now, can we conclude at the 0.10 significance level? So first of all, 0.10 means this number has a change. So let's see what this number is right now. This is 0.05. So this is what it looks like right now. What do you think? Is it bigger than or greater than? Does it match?
Are you talking about the 0.9?
I switched this. This is 0.1 and 0.9. 0.1, 0.9. 0.9 gives me 1.33 and 0.1 gives me the negative 1.33. Ah, where the hold on, I'm having a technical issue here. What happened? Okay, I'm sorry guys. Give me a moment. I have to go back to the question. Come on. There you go back. All right, are you able to see my screen?
Yes.
Okay. All right, so we have another question. We were fine on that one. Let's do another question. Let's go with let's go with this one. Bear with me for a second. I'm trying to get this to go down. All right, there we go. Oh my God, seriously. A session has ended. Let me get this back up. There it is. Oh my God. Sorry. I don't know what's going on with this. Let me click out of it and I'll click back in. All right. All right, let's see this question. Let's see if we can do this one. So here we are. We're doing this one down here. An electrician who has a manufacturing process with a completion time of 65 minutes. I bet you that's the mean that they want to give us. So we'll put a 65. It is claimed that under new management, the mean completion time is less than 65 minutes. So to claim this, they take a random sample of 18 samples. So that the random sample is 18. That doesn't change. Notice that these are all less than 30. They're all like 18 and 17 and so on. The sample mean is 62. That's 62. And the standard deviation is going to be 9 minutes. It is. They want to do a 0.05 test. So in this case, they're going to go with 0.05. And that gives us negative 1.73 and positive 1.73. The test statistic is negative 1.414. That's computed for us. The p-value of that would be 0.087. So what are we going to state as the mu?
Will the mu be equal to 65?
The mu is going to be equal to 65. Good. And what is the alternative hypothesis? I'll give you a hint. If you can see my cursor, you can see it.
The less.
Yep. So
And
you're
so
going to say mu is less than 65. What that type of test? The t-test. How many degrees of freedom?
is it still 17?
Mm-hmm. Yep. What is the value of the test statistic?
Is it the negative 1.4?
Negative 1.414. And the critical value,
0.087676?
1.73. 1.7396 technically.
Oh, so hold on. It's the, is it just the higher number, the positive of the?
Well, in this case, it's gonna be the negative, isn't it? We're about to make the same mistake as last time. So it's gonna be negative 1.73961 technically. And at the 0.05 level, can we conclude that the mean computer completion time under the new management is less than?
Yeah,
You're gonna say yes?
I don't know. I'm just gonna say yes though.
Okay, if you take the absolute value of these, I want you to pay attention to this. Take the absolute value of negative 1.414. Take the absolute value of the negative 1.73. So you're really comparing is 1.414 and 1.73, which is the critical value versus the observed value. The observed value is a 1.414.
So, so we're trying to figure out which one is greater than that? If it's
Yep.
greater than or not?
Mm-hmm. So draw a normal distribution if you would. Let me see if I can get this to draw for me.
But
I'm gonna get this one to go for me. Give me a second. Okay, so here's what I'm gonna do. Here is a normal distribution with the z-score. We have a negative 1.414. Hypothetically, there is a positive 1.414. If I'm comparing it to 1.7396, this is going to be out here, negative 1.7396. Over here, this is the critical value, positive 1.7396. Now, because it's less than, we're going to focus over here. This is your observed value. This is your critical value. This is your observed value. This is your critical value. The rule of thumb is if OV is greater than CV, we're going to reject the null.
so in this case, it would be because the negative 1.414 is greater than the negative 1.7396.
Absolute value of it. So think of it as, is the absolute value of 1.414, negative 1.414, is that greater than the absolute value of negative 1.7396?
No.
So this is actually 1.414 is not greater than 1.7396. So if the OV is greater than the CV, we reject the null. So in this case, we're going to say
No.
okay. We're gonna go no? Okay. So let's check our values. Do you see the big old correct sign in front of there?
Yes.
You should be very proud of yourself. Sorry for the chicken rat scratch. Okay. Shall we do this again? Do I hear yes, teacher? Yes, teacher.
Yes. Yes.
Yes,
All right.
please.
Here we go. I'm sorry for the constant juxtaposing of the screen. Let me make this smaller. There you go. There you go. So a coin-operated drink machine was designed to discharge a mean of 6 ounces of coffee per cup. In a test of the machine, the discharge amounts of 15 randomly chosen cups, hint, hint, 15. These are recorded. The sample mean and the standard deviation were 5.84 and 0.29. They want to do a two-tailed test at 0.10. Two-tailed test at 0.10. What? Doing this. I said the one from when we did the kitchen. No, I'm doing the same thing. All right. Anybody want to talk to me?
So the mu would be equal to 6.
Okay, mu is equal to yes. And what is the alternative? Two-tailed test.
Not equal to?
Yep. So mu is not equal to 6. And obviously this is a t-test. With how many degrees of freedom?
14.
14 degrees of freedom. And the value of the test statistic?
Negative 2.137.
Negative 2.137. Okay, and find the p-value?
0.025.
There you go. And so based on this, at the 0.10 level of significance, which is really the 0.05, I'm going to compare the p-value 0.025 to 0.05. Does the value differ from the 0.0 the 6 ounces? Yes or no?
Yes.
In this case, remember, if p is less than alpha, p is definitely less than alpha. So I would say yes for Dectanol. Yes is going to differ. Are you cool with that one?
Yes, mate.
Yes.
What's wrong with C?
Is it missing?
It's not negative. It should be regular, just plain old. So now what's the problem now? Which answer is incorrect? Partially correct.
It said it was D that was incorrect.
D was incorrect? Okay, okay, too late to go back and change it. Let's do this one now. Let's do this last one. Let's see what you get here. Do we agree? Thus far?
Morris? I'm gonna just say yeah.
Okay, the degrees of freedom. This is 1.744. They're asking us to check this at 0.10. So this is gonna be 0.10 and 90.
I said, mm-hmm.
What's that? All right, what do you have?
The mu is equal to 40.
Mm-hmm. So you have mu is equal to 40. And what did they say?
The mu greater than 40?
Mu is greater than 40. Very good.
Mm-hmm.
And now what type of test?
See?
T-test. How many degrees of freedom?
18.
18. What's the test statistic?
1.744.
1.744. Okay. Oh. Sorry about that. All right. And what's their p-value?
Mm-hmm.
0.951.
Okay. You're going to go with 0.951?
Or 0.950, I guess. Sorry.
Okay. I'm going to go with 0.95. You're going to go with that. So we check this. Let's see what's going to happen. Can we include at the 0.10 level of significance that the mean number of hours is greater than. Is P less than alpha?
Yes.
It's one-tailed.
OP is less than alpha.
Yeah. So yes or no?
Yes.
Okay, you're gonna go with yes. Let's check it. What's the matter with D?
You need 3 or more decimal places.
Okay, so you want to do with 951?
Yes.
Okay, let's try it. Recheck it with that. It's still incorrect. What other number could it try? Greater than. Greater than. Look at look at how I.
Would it be the 1.330?
That's a p-value.
Oh, okay. You're right.
Is it
Let's
the
try to find out-
0.049?
Yeah, let's try that.
How did
Look
you
at
get that number though?
1 minus.
Uh-huh.
1 minus. And all you have to do here in this bottom part is say equals 1 minus the top number, the 9.
And what was the indicator that it would be that number? I'm sorry.
It's greater than.
Okay, greater than.
When it's less than, the number you get is the 0.95. But this isn't less than, this is greater than, which is 1 minus. It's always 1 minus. Any questions on this one? Do you want to do another one like this or move on? Silence means keep doing this. Yes? Do another one? Yes?
Maybe one more.
One more. Let's do one more. All right, there you go. All right, do you wanna tell me what to put into the hypothesis here?
So the first one would be the mu is equal to 700.
Mu is equal to 700. Okay, yes.
And then I know the second would be mu is less than 700.
Mu is less than 700. Good.
Mm,
Obviously a t-test.
mhm.
Degrees of freedom,
13.
13. And the value of the test statistic.
It's a negative 1.78.
Is gonna be negative 1.782. Okay. And the critical value. Now in this case is 0.10. It's gonna be 0.10, critical value.
So it'll be the negative 1.5017.
Let me look at this carefully here. They're giving us an alpha of 0.10. In this case, we're gonna have an alpha of 0.10 and an alpha of 0.9. So this one is gonna be they said less than, right? So 1.35. Let me see something here. So 1.35. Okay, now based on this,
Oh, you gotta put 3 or more.
negative 1.350. So based on this, is it true to conclude that they are less than 700? Remember, draw the normal distribution. Absolute value of 1.782, absolute value of 1.35. If OV is greater than CV, we reject the null.
It's less than.
Huh? Less than? Yeah. So yes or no?
That would be a yes.
You're gonna go with yes? You sure? The
Oh.
OV is less than the CV?
Oh, no, we need to reject the null. So no, sorry.
Actually, you were correct. It's yes. It's 1.350. So if I draw you another picture of the OV and the CV, let me draw another picture. So here's the normal distribution. Okay. So we have an OV of 1.792, which is out here. This is a negative 1.782. The negative 1.350 is going to fall somewhere here. Now, naturally, you would think this would be bigger than this. But if you think of this as absolute value, this is absolute value of 1.350. This is the CV, and this is the OV. In this case, Let's think of the positive side of it. In this case, this is the 1.35. And here's the 1.782. If OV, observed value, here's CV. I'm sorry, reverse that. This is a CV. This is the OV. The observed value is greater than CV. This is the value that you're not going to reject. Remember, this is 0 here. So this goes on positive. This is positive 0.135. This is positive 0.172. Here we're going negative. The bigger negative number is actually this one. You have 1.35, the OV, the CV right here goes in here. That's this one here. This gets erased. So you're going to reject the null or fail to reject the null. In this case, it failed to reject the null. Okay, do you want to try another one?
Okay.
Yes, no? Yes, no?
No, we can move on.
Move on? Okay, in that case, let's move on to proportions. That's these values here. That's the second set of questions I gave you. Okay. So in that case, we're going to look at these questions. Take a look at this question real quick and take a look at your Excel sheet. So an administrator of a rural college claims the proportion P of students who commute farther than 15 miles to school is more than 70, or I'm sorry, the 20%. To test this, she selects a random sample of 270 students of college, and she finds that 70 commute further than 15 miles to school. And is there enough evidence to support the claim at the 0.05 level of significance? So further than 15 miles. So what you're going to do is, the proportion they're looking at, P, this value that I'm circling with my highlighter here, is going to be the 20%. So here you're going to put 0.20. The next number, X, is going to be 70 out of the N value, which is 270. The value that the P hat represents is 0.26. 70 over 270 is 0.26. And 1 minus this is basically going to give you that number. If you look at the proportion, I did 0.2 and 0.8. 0.2 and 0.8 are complements of each other, and you need them in the formula. This is also a formula. So this gives you a z-score here. The z-score is that formula. So you can click on your own screen and get your numbers as you need. Are you copying them down? Or can I take them off screen?
I'm good.
You're good? Okay. So the z-score you get is 2.434. And you have a critical value and you have a p-value, which is, by the way, in this case, you're going to do 1 minus the p-value of 0.99, which is 0.007. You might want to do that for yourself. So we begin with this one. In this case, we're going to say p is equal to, the proportion is equal to 0.20. So the proportion p is equal to 0.20. And here, the proportion is the proportion p is greater than 0.20. And you know that because she states that they commute 15 miles or more, in this case, farther is more. The value of this test statistics is going to be a z proportion. Notice you have these choices of f, the chi, the t. This is going to be a z proportion. And the value of the test statistic, in this case, is going to be 2.434. So 2.434. The critical value in our case, we're going to say is at the 0.05 level. So we're going to go here. We're going to say, okay, we want 0.05. And it's going to be either 1.65 negative or positive. In this case, it's going to be 1.645. And can we support the claim that the proportion of students who commute is further than 15 miles? So in other words, did we reject a null? And we're going to say yes, because obviously our p-value is very small. So if you want to take a look at here, let's take a look at the our p-value is 0.076. Very small p-value. Okay. So this being our data, let's check our values and let's see if we are correct. We are correct. So take a look at what's on the screen. Maybe you need to see the question any bigger. I can move this over a little bit.
So for D, you take the,
Uh-huh.
is that where you take the absolute value then? Because we've gotten negative 1.645.
Yeah, it's either that or it's going to be the positive. So it's going to be the absolute value
Okay,
of this term.
thank you.
So 1.645. Absolute value of negative 1.645. Okay, anything else on the screen that is a question? Now you understand that by hand you can do this. You would follow this direction to get these values. And this formula will give you the p-value, which is basically the sample mean minus the sample divided by the p times p minus q. So I say it's p hat times q hat divided by the sample size. So, okay. You ready for another one? Or do you have a question on this one?
I'm ready for another one.
You ready for another? Okay, here you go. All right, so follow along on the handout here. And the only thing you need to change here, 0.10. So what are they saying?
The proportion is equal to 0.60.
Or
The proportion is less than 0.60.
okay, this is a z-test. What is the test statistic?
Negative 1.853.
Okay. What's the p-value?
1.281 or 1.282.
1 point p-value 0.0
0.031.
0.032 is right here. This one highlighted.
Oh, okay.
It's Norma's dist B16. So can we conclude that it's changed? That it's less than? Remember, it's a one-tailed 0.10 test. If you look at here, this is 0.10. Here's 0.90. Is p-value less than alpha? Is 0.03 less than 0.10? Is 0.03 less than 0.10?
Yes.
Okay. If P is less than alpha, we're gonna reject the null, which means yes, the results are gonna be less than 60. So we're gonna say yes. Let's check. We are good. Are we ready to try another one? Do you have questions on this one? Okay, we're gonna try another one. There you go. All right, let's try here. Here you go. What's the proportion?
0.65.
Yeah, so 0.65. Okay. Now what's the x over n value? What is the fraction?
172 over 260.
Over 260, yes. And that comes to, as a fraction, that comes to 0.66. The complement of 0.66 is 0.34. The z statistic is right here. You see right here. Its complement, you have the p hat, you have the q hat, which is right here, highlighted for you at the 0.35. So now the question is here. This has got to change. This is going to be 0.1. This is now 0.05. Change that one, and that's the new value. The p-value is already set for you. This is already going to be set at 0.65, which is normus dist of the z-score. Okay, so our test statistics is going to say p is equal to 0.65. And what's the alternative going to say?
P is greater than 0.65.
P is greater than
Yes.
0.65. Okay, again, what type of test is it? It's a z-test. That's a given. Now, the z-score. What's a z-score?
0.390.
0.390. Good. And what's the critical value?
Negative 1.645.
Or positive 1.645. Why is it going to be positive 1.645? Because this is greater than. You said this is greater than, right?
Yes.
When it's negative, this will be less. So that's the trick to knowing when to use what. So in this case, you're going to say 1.645. And can we support the criticals, the claim that the students interested in the lecture result is greater than 0.65? So that's when you say p less than alpha. Again, we're comparing this p6 of 0.6517. We're going to compare it to the 0.05. Is the p less than alpha?
No.
We're going to fail to reject the null. So this would be our answer. Are you feeling better about it, or
Yes.
all right? Do you want to try another one? Yes, teacher. There you go. Let's try another one. All right, so what's the alternative? What's the hypothesis?
P equals 0.55.
P equals 0.55, okay. And what's the alternative?
P is greater than 0.55.
P is greater than 0.55. Obviously a z-test, we're good. What's the test statistic?
2.544.
2.544. And the p-value?
2.326.
The p-value.
Just kidding.
Remember, 1 minus or greater than.
Is it the 0.005?
Yep. Very good. Sorry about that. All right. And based on the 0.05055 is 005, is it safe to conclude that more than 55% of high school students in the US use computers for educational purposes? Yes or no?
No.
P less than alpha, we reject the null. Our p-value is 0.05. We're going to compare that to 0.01. Was it 0.01? Yeah, 0.01.
Yep.
Which is a very small alpha value. So is this the 0.05? 005, is that less than 0.01?
Yes.
Yes. How do you feel?
Good.
Do you understand the gist of how we're doing this?
Yes.
Okay. That is our time. I'll go ahead and stop the session for those of you that are comfortable with what I've gone over. I seem to have lost 2 people out of nowhere. With that said, I'm gonna say good night to you. If you have further questions, do you want to stay back and talk to me? That's fine. It's up to you. All right. Good night.
Good night.
Have a good night.
Good night.
Thank you.
Good
Have a
night.
good night.
Thank you.
Okay.